Hi, I'm Luke Roger, and welcome to the inaugural episode of Learned Chemistry, where today I'll be covering some fundamentals of not just chemistry, but science as a whole. This includes the scientific method, atoms, states of matter, the periodic table, and SI units. So let's dive right into it. The scientific method is an empirical method of acquiring knowledge, where researchers or scientists may decide on what to investigate based on previous or ongoing observations, develop a hypothesis, which is a testable statement describing the predicted outcomes of testing, rigorously test this hypothesis by gathering data and information through various tests and experiments, critically analyze and conclude on this gathered data and information, and then, if necessary, modify the hypothesis, retest, and repeat. So an example of this may be cow's milk, where scientists, the general public, farmers, and other stakeholders might realize that calf that drink plenty of cow's milk go on to be strong, healthy, mature cows. So the hypothesis could be made that cow's milk contains all the essential proteins, minerals, vitamins, fats we could ever need to be strong, healthy humans. So various analytical techniques could be used to rigorously test this hypothesis, including chromatography, mass spectrometry, and proteomics, as well as more. And the data of these experiments can be critically analysed and used to conclude on. So in the case of cow's milk, there's no or very little vitamin C. So our hypothesis that it contains all the vitamins we could ever need isn't correct. This brings me to qualitative versus quantitative data. So quantitative data is the number-based, countable, and measurable data we get from experimentation. So an example of this would be my reaction produced 120 milligrams of product and released 400 joules of energy. Whereas qualitative data are observations, interpretations, and are typically descriptive. An example along the same vein would be the reaction mixture changed color from orange to blue. Now I want to emphasize that qualitative data isn't less important. It is still very important and very useful dependent on the experiment or observation. I also want to cover accuracy versus precision. These two terms are used quite interchangeably, but they're not the exact same thing. So an example of a highly accurate but low precision darts game would be the one on the right here. So most of the darts landed around where you want them to be, so they were pretty accurate, but they're all pretty far apart from each other, so it wasn't very precise. Whereas an example to contrast that would be poorly accurate but highly precise game, where all your darts landed pretty close to each other, but not exactly where you wanted them to be. And the worst of both of these worlds would be poor accuracy and poor precision. Science aims for the best of both worlds, where the data and the experimental output is highly accurate and highly precise, as you would in a game of darts. Next, I want to cover some general scientific concepts, starting with the atom. The atom is the smallest particle of a chemical element that can exist, and these are typically consistent of protons, neutrons, and electrons. The image on the left shows where protons, neutrons, and electrons distribute, where protons and neutrons sit centrally in the atom in the region called the nucleus, whereas electrons orbit around the outside. This depiction is closest to Bohr's model, which suggests that electrons orbit around the nucleus in fixed orbits. However, this model isn't the most modern. In the most modern models, that's a bit of a tongue twister, electrons orbit in cloud-like probabilistic regions, where we can't point to exactly where electrons will be, but we can say where they are likely to be. I want you to note the differences in masses between these subatomic particles. Protons and neutrons have approximately the same mass, whereas their electron counterparts are significantly less massive, around 1,837 times less. I also want to briefly explain atomic nomenclature, where X represents elemental symbols, think hydrogen, oxygen, carbon, nitrogen, and Au representing gold. Z is the atomic number, which is equal to the number of protons, and this defines what the element is. A is the atomic mass, which is the number of protons plus the number of neutrons. So this may be represented on the periodic table, for example, like so, where A being the atomic mass is in the superscript position next to the elemental symbol, and Z, the atomic number, or number of protons, being in the subscript position. So, for example, you would have carbon, which has 6 protons, 6 neutrons, so its atomic mass is 12, and 12 in the subscript, 12 in the superscript, 6 in the subscript, and the elemental symbol of C. Or you could just drop the atomic number, the number of protons, because it's essentially also represented by the elemental symbol. So that would be carbon 12 up there. Or you could just have the elemental symbol dash and then the atomic mass. So carbon 12 like that. So this last form of notation is commonly used in the case of isotopes, where it's more important to note the atomic mass than it is anything else. So an isotope is the same element, meaning it's got the same number of protons, but a different number of neutrons. So going from carbon 12 to carbon 13, the atomic mass is going up by 1 because you're adding another neutron, represented by the additional grey circle on carbon 13. And then carbon 14 is adding, again, another neutron. But note how the atomic number does not change from 6. It is still carbon. Carbon has 6 protons. That never changes, ever. You might be wondering, what is the mass of carbon then? You know, we've got a carbon with an atomic mass of 12, 13, 14. What would you put on the periodic table? Would you put carbon 13 because it's the one in the middle between the two? Well, not exactly. We use their relative abundances found on planet Earth. So carbon 12 makes up around 98.9% of carbon atoms you'll find on Earth, whereas carbon 13 represents around 1.1%, and carbon 14 doesn't really represent enough to really come into consideration here. So we calculate the average mass of the element. So in the case of carbon, carbon 12 makes up 98.9%, so you multiply 12 by 98.9%, and do the same for 13, multiply it by its relative abundance, and that'll give you its atomic mass, which is 12.011 atomic mass units. And that's what you do with all the elements on the periodic table. Unfortunately, this table doesn't have their atomic masses displayed on it. My apologies, that's an oversight on my end. But it does still show us the important trends of the periodic table. So going across the table in periods horizontally, the period number defines how many electron shells an atom has in unexcited states. So going across from hydrogen over to helium, hydrogen and helium both have 1 electron shell, whereas lithium, beryllium, boron, carbon, nitrogen, oxygen, fluoride, and neon have 2 atomic shells, and so on. It's worth noting that as you go from period 1 to 2, 3, 4, the atomic radius increases, whereas as you move across the period, the atomic radius decreases. And this is because as you're moving down periods, you're adding more and more shells, so the atomic size is increasing. But as you're moving across a period, the atomic shell number stays constant, but the number of electrons increases, increasing the attraction to the nucleus. Similarly, the periodic table also has groups, which is the vertical arrangement of atoms. And this one's quite important. So the group number defines how many electrons are present in the outermost, which is another word for valence, electron shell. Elements in group 1, being hydrogen, lithium, sodium, etc., have 1 electron in their valence shell, whereas beryllium and magnesium have 2, boron and aluminium have 3, and so on. This goes up to group 8A, which is, we're referring to main group elements here, which have a full octet of electrons in their outermost shell, being 8 electrons. Valence electrons are directly involved in reactions and bond formation. So as you could expect, having the same number of electrons in the outermost shell, or same number of valence electrons, would mean 2 elements of the same group will have similar reactivity properties. And this is because most of the main group elements want an octet of electrons in their valence shell, with the exception of hydrogen, helium, and lithium, where lithium wants to lose an electron to go to the nearest Nobel configuration, being helium. Helium's got 2, and hydrogen wants 1 more, so it can have 2. And this is because it is the lowest energy electron configuration. And again, elements in the same group have very similar reactivities. Moving on to states of matter, being solids, liquids, and gases covered in this lecture, although plasma is another state of matter, but it's not so relevant here, so I'm not going to talk about it. Solids are densely packed particles and can often be in regular repeating or crystalline patterns. The particles are held firmly in place and can vibrate back and forth in a limited space. Contrastingly, liquids are less densely arranged than solids, more randomly arranged than solids, and less confined in space, constantly colliding with neighbor particles. Think of, leaving your classroom after the bell has gone. You might be moving around with many other students, bumping into them, knocking textbooks out of each other's hands. That's sort of like how liquids move around. Finally, we'll also talk about gases, where particles and gases are in continuous motion and are widely dispersed. And inherently, there are fewer collisions between particles at reasonable pressure. Think of how you and one of your friends might be running on a field, very far apart from each other. You're not so likely to collide with your friend. And they have no set volume or shape. Lastly, I want to cover the international system of units. It's important that scientists are able to communicate their research clearly between each other with a set system of units. So a funny example of this is how quite often you might see Americans don't understand European and everywhere else in the world's measurements of distance. So science needs to be rid of this ambiguity. So the SI system was developed, where scientists will use these parameters to define different kinds of measurements. So length is measured in meters, mass in kilograms, time in seconds, temperature in Kelvin, although Celsius is still used but often then reconverted. The amount of substance, which is particularly important for chemistry, is measured in moles, electric current in ampere, and luminous intensity in candela. The SI system allows scientists around the world to effectively communicate their data, information, and procedures with each other, and removes a lot of this ambiguity. Before wrapping up, I do want to talk about the mole a little bit more. The mole is how scientists communicate how much of a substance there is in a sample, solution, or reaction. And that's because it's more useful than the mass quite often. So 1 mole equals 6.022 times 10 to the power of 23 elementary entities, or Avogadro's constant. I almost said it then, but I quite often accidentally refer to it as avocado's constant. And I guess that's kind of a helpful way of remembering it. So a molar mass is the mass in grams of 1 mole of a substance, given by atomic mass. So recall, carbon has an atomic mass of 12.001 atomic mass units. Therefore, 1 mole of carbon weighs 12.001 grams. So another way of saying this is carbon has a molar mass, or molecular weight, of 12.011 grams per mole. And a handy table for working out how many moles of a substance you have, or the mass of a substance, or the molecular weight of a substance, is with this triangle. So whatever unit you're trying to work out, be it the mass, number of moles, or molecular weight, you just simply cover out with your finger either M, N, or MW, and then you've got the formula to work out that parameter. Before I wrap up, I just want to say a big thank you for watching the inaugural episode of Learn It Chemistry. This is a new channel where I hope to provide informative scientific information, particularly relating to chemistry, in clear, concise ways. A subscription to the channel would be much appreciated, as it's quite motivating to help me grow it. And if you have any comments, suggestions, feedback, or concerns, please leave them down below in the comment section, and I'll do my best to get back to you in a timely manner. Once again, I'm Luke Roger. Thank you very much for watching.